We have a limit problem. 2 times n to the power of 1 over n minus 1, quantity to the power of n over n squared as n approaches infinity. And previously, I've worked out the limit of this thing is equal to k squared. So the only difference is that I have k as the base instead of n, and then we have n squared on the bottom. So maybe I can say that since this is approaching k squared, maybe the top is approaching n squared, approaching infinity at the speed of n squared. So we have n squared over n squared. Maybe that's equal to 1. Let's find out. So because, the reason is because, let's first find out the limit of x approach positive infinity of x to the power of 1 over x. Right? So since log of x to the power of 1 over x, what is that equal to? So take down the power, log x. As x approaches infinity, what's its limit, right? So the bottom approaches infinity, positive infinity. So L'Hopital's rule, right? So if we just differentiate both top and bottom, right? 1 on the bottom, top we have 1 over x. Right? What's its limit as x approaches positive infinity? We have 1 over positive infinity. That's 1. That's 0. 0 over 1. Right? 0 as x approaches positive infinity. So therefore, this should also approach the same thing, right? So log of whatever approaches 0, meaning the inside has to approach 1. So meaning this limit is actually 1. No problem, right? So therefore, the limit of n approaches the infinity of n to the power of 1 over n. It's still the same thing, right? Still equal to 1. No problem. So, but then I have to write n to the power of 1 over n into e to the power of log of this thing. Right? Log n. Right? Since, like I said, the whole thing approaches 1, meaning the power approaches 0. That's obvious because n approaches infinity faster than log n, right? That's a well-known fact. So the bottom is a higher order infinity compared with the top. Top always grows slower than the bottom. So that is equal to the Maclaurin expansion nearby the point 0, right? So first term 1, second term, the power itself, right, log n. Then the power term, square term, half of n log square, little o of n square log square. Right, so what again? What's the meaning of little o? So little o of, for example, 1 over n, right? Something is little o of 1 over n if the whole thing approaches 0 faster than 1 over n. For example, 1 over n squared, right? This is little o of 1 over n. Why? Because it approaches 0 faster than that, obviously. Right? And also 1 over n cubed, right, also can be written as little o of 1 over n, obviously. It's approaching 0 faster, right? So little o can be roughly viewed as a sequence approaching 0. It doesn't have to be unique, right? Or, to put it in other words, we can, if this thing, after divided by 1 over n, if it turns out to be still approaching 0, right? What is that? 1 over 10. Is it still approaching 0? Yes, of course. Then we can call this thing little o of 1 over n, right? Meaning it's approaching 0 faster. So this thing actually approaches 0 faster than the inside. Right? Little o doesn't have to be unique. Right? It's some sequence approaching 0. So let's find out the... So like I said, it won't be enough to expand to the first order, right? And second order will be enough, but third order won't be necessary because I've tried it several times already. So then we're going to rewrite perhaps the top, right? Because obviously the top approaches, we have, so 2 times 1 minus 1, we have 1 to the infinity, right? Undetermined. That's why we have to write it down and find out how precise, right? Find out the speed. Like I said, base approaches 1, power approaches infinity. We have to determine the speed at which the base approaches 1 and the speed at which the power approaches infinity. Then we can determine its final outcome, right? So that is equal to e to the power of log of this thing, n times log of whatever that's inside, right? 2n minus 1. Right? So what is that equal to? So e to the power n times log of, so 2 times n to the power 1 over n, but n to the power 1 over n can be written as the following long expression, right? We have to multiply this expression by 2, then minus 1, right? So we still have 1 plus twice of log n over n, right? Twice of that, 2 and 2 cancel out. I have n squared and log squared. Right? Still have twice of little o. But like I said, little o can be roughly viewed as a sequence approaching 0. So 2 times a sequence approaching 0. Is it still approaching 0? Of course. So constant doesn't matter. Still the same thing. Little o of log square. Right? That's what I have. Now, the log we have, inside we have 1 plus. How about this? Hopefully it's approaching 0, right? Like, and of course, higher order infinity compared with log. So this is fine. How about this? Yeah. This is a square of the previous, right? Of course, approaching 0, right? So this, of course, approaching 0. So we have 1 plus approaching 0. Of course, we have logarithm Taylor expansion nearby point 0, Maclaurin expansion, right? So we've rewritten the top into e to the power of the whole thing. So we're going to expand logarithm nearby 0 because, like I said, this expression approaches 0. We have 1 plus something approaching 0. So Maclaurin expansion to logarithm. So e to the power n times, what's the expansion of logarithm? All right, first term, so first term we straight away have this whole thing. Right? Twice log n square log square n plus little o. Right? That's first term. All right. Still, we have to expand next term. That'll be enough. That'll be sufficient. Otherwise, so second term is we have to minus half of the whole thing square. All right. So let's find out. So the like I said, minus half of the whole thing square. twice of log n plus n squared log squared n plus little o of n squared log squared and whole thing squared, right? So, in fact, we don't have to expand it all. All we have to do is to realize the meaning of little o. Like I said, as long as the sequence can approach faster than the inside, then we call it little o. For example, this little o, right? Doesn't have to be unique. So like I said, this guy approaches 0 faster than the inside, right? But this guy is the same as this guy, so we can just easily extract them out, right? Common factor. The reason we can extract out common factors just like normal algebra is easily verifiable. I'm not going to go into details. So twice of log n. All right, factor it out. N squared log square n, right? 1 plus little o of 1. This after we factor this out, we're only left with 1. Little o of 1 meaning this thing approaches 0 faster than 1. So what does that mean? So that means if something divided by 1 can approach 0, then this approach 0 faster than 1, right? So for example, 1 over n is little o of 1. Because 1 over n divided by 1 still approaches 0. So this can be viewed as some sequence approaching 0. So don't worry about this. So whole thing square, right? So 1 plus something approaching 0. So this bracket approach 1. Right? Then we square the whole. So that is equal to minus half. This thing square. N square 4 log square. Right. Then what do we have? We have twice of 1 plus little o of 1. Multiply this, multiply that. Right? Yes. Multiply this, multiply that. Now, we have to square this whole thing. This whole thing. Like I said. So, square this whole thing, it means we multiply, so square this bracket, right? Already approaching 1, right? Then it'll of course approach 1 as well. Now, square this guy, meaning this guy times itself. Now, this guy already approaches 0. Then you multiply by itself, still something approaching 0. So is it approaching 0 faster than itself already? Yes. Because itself multiplied by some infinitesimal. Of course, faster than itself, right? So we have, this will approach 1. Don't worry about that, right? So after we square this whole thing, still we can call it little o of this thing. Little o of this thing. Like I said, we have twice of something that's approaching 1 times, what is this thing? Approaching 0 times this thing. Is it approaching 0 faster than this guy? Yes. Because we have infinitesimal times this thing. So still can be written as little o. Still little o. So we have the little o of this guy plus little o of the same guy, right? Meaning can I combine them into little o of this guy? Yes, meaning can I call them approaching 0 faster than this guy? Of course, because we can simply extract this guy. Extract just like normal algebra. We have little o of 1 plus little o of 1. Still infinitesimal, still approaching 0 times this guy. So still approaching 0 faster than this guy, right? So combine them together, right? So we have this plus that all together multiplied by this, right? Then we have to, so like I said, minus n squared. We have twice log square plus constant times little o of this thing. Still little o. Now, this is easily verifiable. Right? So we have, so this, like I said, is the next term in this Taylor expansion, Maclaurin series, right? Just write this down in there. So minus n squared twice log square plus little o. But like this little o, the same thing, still combined together, right? Then we have to plus little o of this whole thing square. Right, what is this? Right. So like I said, this whole thing square is equal to this, right? Equal to that, equal to this, equal to that. That's before I multiply by the constant, right? So what if I say little o of this thing, little o of this whole thing? So this already little o, right? Already approaching 0 faster than this guy. If we say little o of this, the whole thing, right? Of course, even approaching 0, even faster. Faster than this guy, of course. Faster than the guy inside, right? Again, little o of this guy. This constant, don't worry. Still little o of this guy. So we can call the whole thing little o of just this guy. Right? Right. First of all, approaching 0, faster than this guy. Then faster than this, of course, faster than, so this little o, still combine them together, still, right? So we have this, so minus twice of that, and this can combine with that, right? It becomes just minus. Right? Minus, this is gone. So we have e to the power of twice log n and minus n log square plus little o of n log square. We have this. Notice that this term approaches 0, obviously, right? This term also approaches 0. So just ignore them, right? So they just become e to the power of 0 times e to the power of 0. It just becomes 1, right? Just focus on this guy. Right? We just have to work out e to the power of twice of log n, right? Now, this this expression, right, still have to divide by n squared. N squared can be written as e to the power of log n squared, right? That's twice of log n. Right, we have this. Right. Obviously approaches 1.